Thank you for that wonderful introductions. And thank you for attending today's session to listen to this interesting topic, at least to me. And for the last 16 years of my life in the mining industry, I have seen a lot of change in the way we use data, the way we deal with risk, and the way we deal with uncertainty. Mining has changed a lot. And the way mining used to be done 60 years ago or even 10 years ago is not the same. Risk is perceived differently, and the way it is calculated has changed with technology, with new input, and with the way it is approached. And as mining industry, it is something that cannot be ignored anymore. Now, let's look into it. What are we going to talk about? When we talk about the application of analytics into mining, so we'll be looking at geological uncertainty, the impact of geological uncertainty, and the way we use data to estimate uncertainty in a predictive way, which we call predictive analytics. And we will use some algorithm, particularly the decision tree, the concept of entropy and gain. And we'll look at the model and how do we select the appropriate model, and then apply the concept of real option analysis, which is used to value flexibility. We will analyze the result, and then I will give you a couple of resources for you to go through in case you will be interested in them. Now, geological uncertainty. Every mining company has to manage some level of risk, and the risk tolerance depends with the kind of information you get. Inadequacy, information will never be enough, which is a challenge to every mining operation out there. But to start a mine, you always have a reasonable level of information, which is obtained through resource modeling. Things like boundaries, tonnage, and chemical composition is always known. So there is a lot of also unknown, and there is also knowns unknown. What do we mean? We always know certain things change, but there are things that we don't even know that they exist. So how do they impact a geological uncertainty? Lack of information, of course. When we apply to iron ore, in Western Australia in particular, a lot of deposits come with things like fiber and clay, which choked the processing plant. We has estimated based on our research, 46% of the feed is always made up of clay in the cyclone. And this clay always been processed using what we call descent process. But it is very expensive. Not many companies support it. It's not easily justified. We know of one company in Western Australia owned by FMG, the Cloudbreaks mine, which use the desal plan. Otherwise, you have to work really hard to get the data. But if there is a way to justify such investment, then you could comfortably solve the issues. But do you always have enough data? No. And this is where data utilization come in. Big data is one of the disruption that has been touted in the 21st century as put forward by Deloitte Economics in 2016. So predictive analytics is used to manage geological uncertainty in mining operation and to create managerial flexibility where you can make decisions. But there is a disconnect between technical people like mining engineers and those who manage data. The big question is, can predictive analytics provide feasible solution in dealing with the internal uncertainty that result in operational risk? And I think there is a possibility, and we tested in our result. So in this analysis, we will look at the decision tree, which we have mapped the root, which is a form of classification. It is different from statistics. As you can see, anything in green is showing our path that we have taken to decide on what classification model we will use. And decision trees are easy to visualize. You can see it and you can intuitively connect to it. That's why we go with it. And we will apply a certain processes and methodologies in order to apply the decision trees in a manner that is understandable technical people. And I assume in this room there may be many people who are not technical. So let's look at the process. Like any other analytical process, you just start with the data. Where is your data? And we'll get a data from warehouses. You have heard of the data archiving, the data storage. And we process this data and look at the anomalies in it. And then we'll apply real option. We project this in form of a tree. We project it in form of element in a ore block within an iron ore mine. And you see alumina and lump, which we'll explain in the next section, are the main predictors of a variable such as clay occurring in this particular case scenario. So we are applying it to a real case. So we picked a number of ore block in one of our case studies, and we withhold the name blocks, and we apply a certain qualitative look at it, and we realize that there are main variables which are iron, silica, alumina, magnesium, calcium, phosphorus in a ore block, which are of influence. And then they tell us the risk, and the risk is, can we intercept a clay block? Because the clay is a risk. When it gets into your processing plant, it choke it. So processing risk is our target variable, which we are creating in our model. I know this may be confusing at this stage, but we'll work through it slowly to understand how it is applied. So geologists at every mine site and mining engineers usually have a fair idea of what is risk block and what is not risky. So they look at the thing like lump percentage. Lump is when the mine material that is mined out of the earth, fine material, is lumpy. So they will grade them in terms of processability from low risk to very high risk. And then if it is low risk, you do nothing. If it is a high risk, then you create an option which is a blue columns in this picture. So we have to categorize the data. So we create a categorical data in terms of risk, low risk, medium risk, high risk, and very high risk. So let's look at how do you apply that. Now we said we are applying a decision tree, and we'll use the concept of entropies and information gain. What we are saying here is that the data set is subdivided into small group of similar values or with homogeneous properties, and their entropy is calculated, which is the information gain. If the data set is completely homogeneous, an entropy is 0, whereas an entropy of 1 apply if the data is equally divided. But entropy of attribute such as Fe, if it is gaining, then we say the probability of the attribute is occurring, and we use the logarithm, which we change to a natural logarithm of number n for any variable classes in the model. Now, how do we calculate entropy of a ore processing or risk as per the equation which we have just looked above? So the equation applied to calculate the entropy of a ore or processing risk based on the sample size of 35 before. So we look at the sample size and we find that 6 blocks are very high risk, 5 blocks are high risk, substantial risk is in 2 blocks, the moderate risk were 4 blocks, and 18 blocks were low risk. And when we run some Python code in Orange program, so we wrote script of code in Python program, is a language for data analysis. Then you can see the tree there. We see that the percentage of the material tell you about the risk. So let's look more about the entropy of processing risk as per the equation. So the decision rule and decision node identification is very important when you are making a decision. How do you decide which one is good or which one is risky and which is not risky? We'll use the frequency table and the summary of calculation for each block in terms of processing risk using the other predictors. So if you look at it, it may look a little bit smaller here, but you see that we categorize the 5 variables in terms of lump percentage, in terms of clay occurring in the block and the water tables and silica, and we break it down based on our Python code, and we realize that all the run, they did not give us good results except the classification tree. So that is how we choose that model. So we look at it, and the classification tree gave us close to 80%, as you can see in the probability graphs above. So the highest could be 100%, which no model could achieve easily unless you recalibrate it several times. So our idea here is not to accurately pinpoint, but to give us a direction of what we expect to occur when we dig a block. So when we go and dig a block, we want the model to tell us that whether it's going to be risky or less risky, because we don't want to choke our plan or lose production, because any bad block will block the cyclone in processing plan. So now we have known, we build the model. How do we apply to make we build the model? How do we apply to make decision or create flexibility such that managers can be able to turn on and off a certain section of a mine? So we look at effective utilization of the plan, and we realize effective utilization is 75%, 90 to 93% of availability, operating efficiency, and the schedule loss and probability of intercepting the clay material is 78.6%, which we calculate in the model. The ore recovery normally range between 80 to 90% for most iron ore mine because it's mass production. Operating cost of a saleable ore product, that is what is processed, going to the market, is 47 to 43. This was in 2015 and 2016. But then we have to statistically put it into perspective in terms of a real world, that when you go and dig a block, it's not going to come the way you normally calculate. So we use what we call the Poisson's model or probability theory, that every truck arriving loaded with problematic ore will occur one at a time. And in stochastic process, work on the premises that event occur one at a time in a successive period, and the timetable is between 0 and t, such that probability of event x occurring is the function of fx dot t. Events are mutually exclusive. No two will occur at the same time, and then events are disjoint in terms of probability. So look at the real option analysis and the result. Analysis of a traditional non-flexible mine, that is assuming normal operation. You are not using predictive analytic. We run the model. We see that the project value of this particular iron ore, and this is a real case, by the way, in Western Australia, and we withheld the name because of confidentiality, was $113.8 million. That is over 2 years period, between 2015 and 2016. If you run this mine with the parameters in the table, then you are getting almost $114 million. That is what you will get. The mine is not flexible. If the bad ore get in there, bad luck. Then, the real option analysis, we also have to look at the simulation. Anything could happen. It could be good, it could be bad. So when we run a simulation, Monte Carlo simulation of the crusher feed for an unflexible ore, we realize that the mean was 111. So that means our traditional mine model of discount cash flow was overestimating the production by $3 million. For a small mine, it does make a difference to the shareholders. Then the results are spread with 302,000. That is almost $250,000. Slightly $350,000. That's what it means. Now, we have looked at those. Let's create flexibility. How can managers manage the mine flexibly? Like, how can managers manage the operation without losing money or production, which is very important to the investors? So we said, store a lot of material in terms of bin, and we call them stockpile. That means dig everything continuously and keep storing them, and pay the cost of stockpiling at $4.5 per ton in terms of US dollars. When we run the simulation on that, we realize that the project value of this mine was 138, which is almost $140 million. And then the standard deviation, the spread of the result was 59,000. The spread of the result was 59,000, which is actually good result compared to the previous one. And then there was another scenario, and we said, instead of digging everything and stockpiling, why don't you create additional area of mine that if this area is bad with problematic ore material, then you go to the section of the mine where you can dig and still be able to process. And we realized that the result was slightly lower, 127 million. So stockpiling was better. And then the spread is wider, 73,000. As you can see, that is mean we want to get 95% of the result. So, looking at the previous one, paying the cost of drilling an additional site is 15% of the cost. Now, creating flexibility by building a bypass circuit, that means if you build a bypass circuit, assuming that you don't have to worry about processing ore, problematic ore which has clay. If this area is blocked, then your circuit can flow bypass. And by paying for it, we create a value. But then you have to put a capital cost of 6.8 million in order to build the bypass. So nothing is coming free. You pay cost for everything. And we realize that the value is 131. Better than just creating additional area, but it's slightly lower than just stockpiling the material. Now put everything together. Compare all the 3-4 options. By rehandling the material, which is mean stockpile and rehandle them, you increase your value by 21%. But bypass circuit, which is 16%. So the optimal decision would be build a larger stockpile system. And how do you arrive at that? Because before we have to calculate the risk by using predictive analytics, which was 78% chance of getting the block classification correct, whether it's risky or less risky. And that will increase your project value by 21%. In other words, you don't have to guess or make decisions based on deterministic approaches. So machine learning can assist operation to create flexibility. That is a significant value addition. And when we talk machine learning, we are talking predictive analytics, which can help your analysis in terms of creating real option. Because when you know the risk, you can create option. Additionally, justify and help managers to move away from what we call scorecard fever. In one of my papers, we call it scorecard fever, where managers are struggling to meet the short-term KPIs and sacrifice the long-term value. When you can justify, you are good. Geological uncertainty is real and it's going to remain within the mining industry. Therefore, if you are to help and create value, a substantial value in the modern era of the data science, then you have to use your data. It is a real source of value. For anything to do with mine planning, operational support, sustainability planning, data analytics and management consulting, software and training, please feel free to contact Dufico Consulting. We are based in Western Australia. Some of the biggest names in the industry are our customers. We are working with companies like Rio Tinto, BHP, Mineral Resources, and many other small operators. We handle the whole project value chain from upstream activities to the downstream. Additional resources, as I mentioned and promised before, you can also go and read about some of the work. The top 2 papers are my papers, which are published with reputable journals, the resource policy journals, and plus the work of other reputable colleagues in the industry. So, feel free to reach out to us. And our contacts are available at Dufico Consulting. You can Google it. As you can see the logo at the top bottom left corner. The big D of blue and red is our logo. and we will be more than happy to assist you. Thank you for listening. I'm Dr. Ajak Duany Ajak.